Okay, I got a request to go over tonicities with you guys. Apparently there is some confusion on tonicities, which, to be completely fair, is what there is always confusion over on in this unit. So if you find tonicities confusing, and by that I mean isotonicity, hypotonicity, and hypertonicity in regards to what they do to the different cells, you are not alone in your confusion. So I'm going to actually go to your lab module first, and we are going to look at a few things here. There is this video, Effects of Osmosis on Living Cells. Osmosis and tonicity go hand in hand, okay? Osmosis is water flow across a semi-permeable membrane. That is the definition of osmosis. Depending on the solute concentration inside or out of the cells, the tonicity changes, and so where the water flows changes to and from inside or outside the cell. So solute concentration is really what drives tonicity, and then depending on if you're in isotonic, hypertonic, and hypotonic solutions, the water is driven one way or another across that semi-permeable membrane through osmosis to either dilute the solutes inside the cell, dilute the solutes outside the cell, or do nothing because the solutes are equal on either side. What we call what happens to the cells are different things depending on if it's a plant cell or an animal cell. So the person talking in these videos in your lab modules, by the way, is one Miss Jordan Slope, or Mrs., I'm not sure, but she is in charge of the North Lake labs, the biology labs, specifically over on the North Lake campus. She is a wonderful resource. I don't think you're ever really supposed to contact her individually, but if you are just like in a jam and I'm unresponsive, maybe an email to Jordan Slope. You'd have to be able to find her though. So it's not recommended that you contact her. I am your teacher of record, so it's supposed to all go through me, but I'm just saying. Well, the first thing they look at in this video is plant cells. And so the first thing to do is put it in a 20% sucrose solution. Did I push play? I did not. And so those words pop up right here. And you see immediately, did y'all see that? And let's go back. See how the cells are nice and full. They're out of focus here, but they're nice and full. And then watch what happens when that 20% sucrose solution hits them. Okay? This has created, did you see that word right there? A hypertonic environment. I'm sorry that just happened. Hypertonic environment. And so you can see that the cell membrane, this is now the cell membrane of this cell, and here's the cell membrane here, and here. You can see that they're pulling away from the cell wall. This is called plasmolysis for plant cells. That's what we call it. And what's happening is because there's so much sugar outside the cells compared to inside, the water is being driven outside the cell across that semi-permeable membrane, and the cell is shrinking because it's losing its water. And we call that plasmolysis, or a plasmolyzed cell when it's a plant cell. And as long as you keep it in the sucrose solution, the cells will continue to shrink and shrink and shrink. You can see how much clearer the border between the cell wall and the cell wall and the cell membrane is getting here. Okay, so then we'll let this run, plasmolyzed cells. Look at them just shrink and shrink and shrink. Now we want to reverse this effect. And so she's going to add distilled water to the slide. And as she adds distilled water, watch that. Let's go back. As she adds distilled water, the solute concentration outside the cell changes. The sugar is being diluted. And so now there's going to be more solutes inside the cell than there were outside. So the water will be driven back across that semi-permeable membrane to inside the cell, and the cell, in this case, can re-expand and continue functioning as a normal cell. So this is plant cells. I'm going to do a physical hand-drawn demonstration of this exact same material. But in a hypertonic solution, that means there's more solutes than water outside the cells. So the water wants to go and dilute those solutes outside the cells. And so it leaves the cell and you get a plasmolyzed cell. In an isotonic environment, plant cells aren't exactly really happy because plant cells need full vacuoles of water, and isotonicity is equal movement of water inside and outside. The solutes are equal on either side. So we call it a flaccid cell. So this would be a wilted plant. In a hypotonic solution, you get something called a turgid cell, where that water vacuole is completely full of water, as full as it can be. And that water in the vacuole is putting pressure against the cell walls, and the cell walls are putting pressure back on the cell. And so they are completely filled up. This is a happy plant cell. And they become turgid. Animal cells work differently in these types of environments. So let's look at animal cells. We usually look at blood cells, horse blood cells or sheep blood cells, either one. And did I push play again? Yes, okay. So here in 0.9% NaCl, it's an isotonic solution. And you see, not super clearly, but you see these very happy blood cells that have that nice little donut shape to them. They have that donut shape because blood cells are anucleated, which means they don't have a nucleus. That's the normal state of a red blood cell. And that is to make more room for hemoglobin to carry oxygen. And so they're very happy, nice donut-shaped cells, just like they should be. Now, if you increase the salt in the solution, you create a hypertonic solution. So the water inside the cell will leave the cell to try to dilute all that salt outside the cell. And you get what we called crenated cells. They have shrunk and they are crenated. This effect can be reversed and you can live if you act quickly enough. But these red blood cells are not functioning, cells are not functioning normally, so they are not carrying oxygen like they should be. And so we have crenated cells here. Now remember, in plant cells, this was called plasmolyzed. Here it's called crenation. It is important that you know the different words. Then, okay, there's your crenated cells. They fold in on itself and over itself as well. Still some crenated cells. Then you can put animal cells into a hypotonic solution. We do not have cell membranes. Yes, we do. We do not have cell walls is what we don't have. So we don't have something to stop our expansion like plant cells do. We do not, excuse me, enter a state of turgidity. We explode. Animal cells explode when they get too full of water. And so here, if you look at them, you can see the shine on these cells. Let's go back just a little bit. No, too far. Okay, you can see how shiny and full and round these cells are. They become large and more spherical, eventually to the point where they lyse or burst open. What we get then is called ghost cells, specifically when you're talking about red blood cells. And you just get these remnants of cells that no longer have the hemoglobin inside them because it's been lost to the environment because it's burst out. So here's a ghost cell, which is just the cell membrane of what used to be. So here in a hypertonic solution, we have crenation. The water has moved out of the cell to dilute the surrounding solutes. Here we have nice, happy donut-shaped cells like they should be. And here we have swollen and lysed cells. You can see this one is burst. And that is because the water has flown into the cell to dilute the solutes on the inside of the cell. So this is what tonicity is. And I'm just going to repeat all of this again when I draw it out for you. Okay, so I think that's the end of this video. Yes, all right. So let me stop share. Yes. Okay, So now we are on to my camera thing. We're going to do the same thing. We're going to talk about tonicities. And so here I have 3 cells ready for you to go. So the first one we're going to talk about is always the easiest one, isotonicity, if I can spell it right. Iso means equal. That is what iso means. So equal tonicity is, I'm going to use actually a totally different color because that's too close to what I have. I'm just going to use black, I guess, or whatever this is. This to represent my solutes. And all I'm going to do is put dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 dots inside my cell, representing some solute. I don't know, glucose, if you will. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Outside the cell, my solutes are equal. What this means is that this color is representing water, is that water is entering and exiting the cell at equal rates. That is good for the cell, and so the cell just stays a happy cell. This is animal cells specifically, but the cell doesn't change. It just functions normally like it would in an isotonic environment. For human beings, an isotonic environment is 0.95% NaCl. Okay? We're happy there. We are slightly salty. You all a little bit salty. That's what I'm saying. Don't be so salty. But also be that salty because that's what you want to be to maintain life functions. Now, we're going to go over to hypotonicity. 2 things about hypo. 1, hypo means below, is what it really translates into. So we're below tonicity. Also, hypo sounds like hippo. So they get big and fat like a hippo. And I'm not calling hippos fat. I'm not discriminating against hippos, but they get big like hippos. Because what is happening in a hypotonic environment is my solutes are okay. And let's say that's normal for the cell. But outside, my solutes are, I have very few solutes outside the cell. What this means is that water is going to flow from high concentration to low concentration. Low concentration is inside the cell at this point because there's more solutes than water compared to outside. So water is going to enter the cell at vastly higher rates than it leaves the cell. This causes the cell to swell and then burst. Oops, where's my cell membrane? This is lysis. Lysis means to burst, and this equals death. Death of the cell, and if left to go on too long, death of the human being. Because the water rushes in, we do not have cell walls to stop ourselves from expanding. We expand to our reaching point, and then we burst open. Then you have hypertonicity. It is the opposite of hypotonicity. Hyper, by the way, means above. That is what the Latin translates into. I don't have a fun word play for hyper, sorry. So in this case, we have, whoops, our normal 10. But outside, we have way more solutes than inside the cell. What this means is that water flows out of the cell at a much higher rate than it is flowing into the cell. We lose water and we do something called crenation, or we crenate. Crenation is the action, crenate is the word that you get. And so our cells shrink and there's no, let's say, cytoplasm really left in the cell for organelles to function normally. This can be reversed. This cannot be reversed. Okay? Lysis cannot be reversed. Crenation can. You have a time frame. You're limited here in order to keep this person alive, but you can do it. That one, not so much. Okay? So this is animal tonicities in a nutshell. Iso, equal. Everybody's happy. Hypo, large, big. Your cell swells and then they die. Hyper, small, tiny. Your cells shrink, can't function normally, and then you also, yes, could die from this as well. Plant cells have a cell wall. I'm sorry for my atrocious handwriting. It used to be better, but now it is what it is. What this means is the cell size never changes. I know that my outlines are all different sizes and shape. Let's pretend like they're all equal, okay? I'm not so great at drawing hexagons, apparently. Like, look at this guy, what happened? But the cell size doesn't change because the cell wall will not change. Excuse me, I have to sneeze. Let me pause sharing. Well, that's annoying when you have to sneeze, but then you don't. That was annoying. Okay. In isotonicity, animal cells, happy, even, equal. We like isotonicity. Plant cells are okay-ish, okay? Because what happens is that cell membrane does change size. And so it's just like slightly off. Let's just say that this is a hexagon. It's just slightly off. It doesn't fill the cell completely. So the cell is not experiencing turgidity. It can collapse a little bit because the cell membrane is not pushing against the cell wall. And so we get something that's called flaccid. I'm spelling it wrong. Flaccid. Here, flaccid means limp. Actually, that's what it means. And so the plant goes limp, and we actually call this wilted when we're talking about a plant. And there's not really a way to show this, but it's just the cell membrane is not fully against the cell wall. The cell is living. The cell can survive in this state. The plant can survive in this state. It's just not the happiest it could be. In hypotonicity, where water is rushing into the cell, we call that in animal cells, we burst and die. Plant cells, this is what they want. They want to be hypotonic, because what hypotonicity does for a plant cell, which I guess I don't need the second set here. We'll just do the guys on top. There's a vacuole in here, right? I guess I should put that also on this one. So this vacuole is not as filled up. This vacuole is full. With a full vacuole in the plant cell, you are pushing against the cell wall. The cell wall is pushing back on the cell. It is as full as it can be. We call this turgid. Turgid means swollen. So this swollen cell is a happy cell. This is where it wants to be. They want to be in hypotonicity. We want to be in isotonicity. Finally, hypertonicity. The same thing happens as happens to animal cell. We crenate, but we don't call it crenation when it's a plant cell. We call it plasmolysis. Okay, and so the cell Membrane shrinks all the way in, so where there's no water left in the cytoplasm. So just ignore these. And the cell cannot survive in this environment. It wilts, but then it also dies because there is no life functioning happening in hypertonicity. Okay, I'm going to stop share, and then I'm going to go back to your lab module. And we had questions about the assignment. So, after sitting in a bathtub for hours, your fingers look like prunes. This is an example of osmosis. Water is leaving the cells in your fingertips and going out into the bath water. Your bath water will have less solutes than the inside of your body. So water leaves. So osmosis. So that's actually a the cells are hypertonic to the solution. The girl sitting in front of you, you smell it, that's diffusion. That's solutes diffusing through the air. To get rid of slugs, you sprinkle salt on them. I used to do this as a kid. Growing up and learning about it as an adult, it's a torture. You're basically torturing an animal. Don't do it if you could, please. But that's osmosis because you're causing the water to leach out of the snail because the salt is pulling water out of the snail. You can smell something on somebody else's grill, that's diffusion. Those stupid water things in the grocery store that always turn on the second you reach for your vegetable in the produce section, it's like they know, that's osmosis. The reason they do that is to make vegetables look like they are healthier than they actually are on the supermarket shelves. Water will osmose, is that a word, into those vegetables from the outside, making them look plumper than they would be. Okay, concentration is the amount of solute in a solvent. Crenation is when cell membranes shrink, but only animal cells do we call it crenation. We call it plasmolysis when it's plant cells. Hemolysis, hemo means blood, lysis means burst. So hemolysis is the bursting of a red blood cell. A selectively permeable membrane allows some substances to easily move across while excluding others, also known as a semi-permeable membrane. These were the questions you all struggled with, and it's all just about reading what they're asking. I also agree that they were difficult questions, but I would not have got 100 on this assignment is what I'm saying if I had just taken it probably like y'all did. But if you read carefully, then you know what you're asking for. They are asking for 10% NaCl inside the bag, 10% NaCl inside the beaker. We want to know the tonicity of the dialysis bag. It just so happens that it's equal to the outside. It's isotonic. We want to know where the molecules of albumin will move. Albumin. Albumin is a large protein. Albumin is not allowed outside a membrane, which means that albumin will not move in this situation. So even though it should move outside the membrane, normally is what it would do, it can't. It physically cannot. So in this case, it will not move. 25 sodium sulfate inside, 25% inside the bag, 13% sodium sulfate in the beaker. We want to know the tonicity of the beaker versus the bag. In this case, there's more solutes inside the bag. The bag is hypertonic to the hypotonic solution. There's less solutes in the beaker, so the beaker is hypotonic. 45% water in the bag, 59% water in the beaker, tonicity of the dialysis bag. 45% water means there is 55% solutes in the bag. 59% water means there's 31% solutes in the beaker. 59 solutes to 31 solutes. The bag is hypertonic to the solution. 5% NaCl in the bag, 13% NaCl in the beaker. Movement of the solute. The solute is salt. We actually know that salt can cross the dialysis membrane. You know if you watched the video earlier in the lab module. So the salt will move from the beaker to the dialysis bag. And then this table, I haven't really even bothered to read this table, but dye with a low molecular weight moves faster, true. Movement of solute molecules is faster at lower temperature. False. Temperature increases. It doubles the rate of enzymes. It doubles the rate of movement or something every 10%, every 10 degrees. This experiment is an example of apparently diffusion. I should really read this answer. Temperature can affect the rate of diffusion. What? Oh, A, B, C, A, right, okay. Okay, so temperature can affect the rate of diffusion, true. Aniline blue diffuses at a slower rate because of its low molecular weight. We see aniline blue has a high molecular weight and it diffused. So it diffuses slower because of its high molecular rate. So this is false. So that's that assignment. And let's see if I want to bother going through any of these. Nope, not the options. Test. So you'll get 15 questions out of a pool of 31. So it's possible you don't get the same questions as your peers, which minimizes cheating. Ha ha ha. This crenated, hypotonic, plasmolyzed, y'all need to know these words. What is the tonicity of the beaker in comparison to the bag? The beaker has 80% water. The bag has 60% water. This should be hypotonic, and it is. The bag has more water, it's hypotonic. Which direction will water move? There's 90% water in the bag, there's 65% water in the beaker. The water will move from bag to beaker, etc., etc. And then these questions all here, which the whole thing doesn't pop up. What is the tonicity of the solution in the first beaker? Everything is equal. So what is that tonicity? What is the tonicity in the solution of the second beaker? Water is leaving at a much higher rate than it is entering. What is that tonicity? The third beaker will be opposite. Water is going in at a much higher rate than it is leaving. So what is that tonicity? Okay, so y'all should know all those answers. So hypertonicity, hypotonicity, isotonicity, I hope it clears it up. It's okay if you are confused about these concepts because they're brand new to you for the most part, and also they can be confusing. You think you got one right and you've actually flipped the information. Make sure you are always reading the question. The question can be tricky. It could not be asking you about the solutes or solution of the outside, but the inside, which changes the answer. It's the opposite answer then, unless it's isotonic. So read carefully and good luck with everything. Thank you.